for the first problem, there, for the first problem, we have this setup where yes, we have this setup of a mass here, and there is a they are connected by a string like this passed over two pulleys here, and then there is also a central mass of 2m here. Both of these masses are m, like this. And so at first, this system is at rest, and before they are all released. And so we want to calculate the velocity of this mass 2m once it hits. I believe. Oh, actually, it should have. Okay, actually, the mass 2m is originally here at the top. Is originally here at the top, connecting the string here, and it eventually falls to the tabletop here. And so, yeah, and so this entire distance is 50 centimeters, and so is so are these two distances. Okay, so to solve this problem, we want to use conservation of energy, because we want to find the velocity of something, and we also know the positions of various other objects, which allows us to apply energy perfectly. So then, when the mass 2m reaches this tabletop here, then it's moved 50 centimeters, and the difference in the rope length is, if we only consider half of the setup, then it looks like this: the mass 2m here and a mass m here. And so then this is the new rope. This diagonal is what the rope looks like now, while this horizontal part is what the rope looked like before. And so since we know that these sides are both 50 centimeters, then this diagonal is 50 root 2 centimeters. So then the difference in the rope length is 50 times square root 2 minus 1 centimeters, which is also the same as the difference that this ball of mass m moved from like this position to here. And it's the same on the other side for obvious reasons. So then we can now we just need one more thing to apply conservation of energy, which is the relationship between the velocities of the larger mass and the two smaller masses. So now, if this smaller mass m has velocity v, which is going up, then this big mass 2m has there's also a velocity v going into this mass of 2m, as you can see, and it's the same on the other side. So there's another velocity of v here on the mass of 2m, And so both of them are at diagonals. And so then you can see that if we split these two velocities of v into their horizontal and vertical components, that the horizontal components both cancel out. So they just add together to form one velocity. Let's say, actually, let's call this v going down. So now it should be pretty simple to find the relationship between v and vm, which is basically the vertical component of vm is just vm over square root 2, because it's basically just vm times like sine theta, which in this case is 45 degrees. And this is also vm over square root 2. So added together, it becomes vm square root 2. So that's what v is equal to. Okay, so now we have everything we need to apply conservation of energy, which is basically the energy from these moving masses added together, and then also the energy for the gravitational potential energy added together. It should all be 0, basically. So then the kinetic energy is, we know that's just 1/2 mv squared for a mass m moving at velocity v. So then for the large mass of for the large mass 2m, it would be 1/2 times 2m times well, let's say v, because that's what we're solving for, times v squared plus, and then there are two smaller masses times 1/2 of m, and we know that this would be v over square root 2 squared. And so then what we also know is that the large mass has moved down. And so when that happens, the gravitational potential energy becomes smaller. So then minus the difference in gravitational potential energy. And this is just for a mass of m at moving a distance of d would be like mgd. So then the large mass 2m has moved down a distance of 50 centimeters or 0.5 meters. So then this would be 2m times g times 0.5. And then, however, these two smaller masses m have both moved up. So then you would have to add them again, 2, and then times this one would be mg times, we already found earlier that they both moved up by a distance of this 0.5 times square root 2 minus 1 meters. And so this has to be equal to 0, because at the initial setup, you can use the initial setup is 0. So, and normally there would also be a gravitational potential energy for all of these masses. But if you just set that to be 0, you can just take the differences as we did here and let everything cancel out. Okay, so then now we can just solve this equation. We get 1/2 times, well, we don't need that actually. We get mv squared plus mv squared over 2. This has to be equal to 2mg times 0.5 minus is 2mg times 0.5 times square root 2 minus 1. So this first part obviously is equal to 3mv squared over 2. And the second part we see is we can calculate this is equal to mg times square root mg times 2 minus square root 2. So then now we can just solve for b. Just cancel m out m, and then we have b squared is equal to 2 over 3 times g times 2 minus square root 2, or which gives us that b is equal to just the square root of this 2 over 3 g times 2 minus square root 2, and this is about equal to 1.96 meters per second. So that's the answer for v. Okay, does anyone have any questions about this problem? The problem too is that there is this loop of wire like this that has a current in it, current I, and when this has radius r, there is a point P above, and this distance is 1/2 r, and so we want to find the magnitude of the magnetic field B at point P. So here, so basically the way we solve this is we can basically just apply a law called Biot-Savart's law, which states that this B is equal to mu0, which is a constant, over 4 pi times this integral of I dl cross r over r cubed. Yeah. So then this small r, by the way, is the distance that is the distance of the point to the to the current I that we're measuring. So because basically this law is tells us the this magnetic field at a point where there is another current I somewhere. So r is just the distance between the two. And so now basically we can just apply this. So this would be, then we could use then dB is equal to mu0 over 4 pi times I dl cross r over r cubed. So then dB, the magnitude would just be mu0 I times dl over r squared over 4 pi r squared. Yeah. Okay. So then, so if we want to find the direction. So first of all, we want to find the direction of the magnetic field at this point. When we have a loop here and the current, let's say at this point the current is going this way. So basically, we just look at this dl cross r part. Well, this IDL cross R part. R is like this thing, while this is like well, this is DL, and this is R. So then if we, to find the direction of this cross product, we use the right-hand rule. You put your thumb along the DL vector and your index finger along the R vector, then your then your palm points in this direction outwards. And so basically, since we have to take this for every single point on the loop and add them all together, we can see that most of the components just cancel out. In the end, they just add together to form this. So the direction is upwards. So then we to add them all together, so basically we add all of these dBs together, but we only want to take the component that's like goes up, because all the others get canceled out. So then it would be B is equal to integral of dB, but only the vertical part. So this is just equal to integral dB cosine theta, where theta is this angle. Yeah. And so then to finding cosine theta is pretty straightforward. Looking at this here, this is the vertical distance is r/2. This is r. So then this diagonal would be this diagonal would be square root 5/2r, which we can find by Pythagorean theorem. So then this cosine theta would just be r over square root 5/2r. So this would just be this integral dv times 2 over square root 5, because yeah, basically cosine theta is equal to 2 over square root 5. So then we have this integral, but it's like this might look pretty hard at first, but you can just see that for every single point on the loop, it's the same. So there really is no actual calculus involved. You just basically multiply by the length of this entire loop because it's constant. So then it would just be dB times 2 over square root 5 times 2 pi r. So we can now just plug in our expression for dB, which so we get mu0 times I over 4 pi r squared. This dl, by the way, is just the small parts of the loop. It's just a very small part of the loop, and that's the part we add up. That's the part that we add up to get 2 pi r. So then it's mu0 I over 4 pi r squared times 2 over square root 5 times 2 pi r, I believe. And so then this is 2 pi r actually. And of course, this small r in the denominator of this dB, this r, as I mentioned earlier, it's the distance from the current to the point that we're measuring the magnetic field for. So in this case, we already calculated it. It's square root 5/2 times big R. So then we just end up getting this is equal to I over 4 pi times square root 5/2 R squared times 2 over square root 5 times 2 pi r, and this ends up being 4 mu0 I over 5 times square root 5 times big R. So that's the answer for the magnitude of the magnetic field at point P. Does anyone have any questions about this problem? Okay, I think if no one has any questions, then that's it for me, I believe.